Before we start, who here has heard about Spark? Raise your hand. Okay. Who here has heard of Kmeans clustering? Okay. Who knows how Kmeans clustering works on large data sets? Okay. All of you who raise your hand to all three should go because you know what this talk is about. But maybe I can tell you a little bit more about it. Some quick about me. My name is Sandy. I work at Cloudera on our data science team. Before that, I was leading Spark development, and I'm still very, oh, that's me. Still very active in contributing to Spark and sort of working on Spark use cases on the Hadoop platform. Before that, I was working on Hadoop itself. And before that, I was a WE undergrad. So ultimately, this talk is about when you have lots and lots of stuff. And when you have lots and lots of stuff, you want to kind of try to figure out how to make sense of it and hopefully use it for something that is cool. This is where large-scale learning comes in. How do we define large scale? As a sort of systems-y person, I like to think of large-scale learning as learning where you basically require distributed systems to help you process the volumes of data or the level of computation that is required to tackle your problem. What do people use this stuff for? Some of the most common stuff we see at Cloudera are analyzing all the network packets that go over a network and trying to detect evil network activity, network intrusions. Ditto for credit card transactions. Analyze every transaction that goes through your payment system and try to predict fraud and see evil things that are happening there. Movie viewings, the classic Netflix challenge situation. You want to be able to do recommendations. So step one for most machine learning prediction problems are try logistic regression. And sometimes logistic regression works really awesome for what you're trying to do. Other times, logistic regression is terrible. And when this happens to you, it's usually time to try to understand a little bit more about the stuff that you're dealing with. So for example, how many kinds of stuff are there? Why is some stuff not like other stuff? How do I contextualize new stuff when it comes in? And is there maybe a simpler way to represent this stuff that allows us to think better about the differences between it? And so for this, we have unsupervised learning. We have algorithms and approaches that try to take data sets and learn the hidden structure inside data, and then use this hidden structure to interpret new data as it relates to this structure. Unsupervised learning sort of broadly breaks down into clustering, where you're taking a data set and trying to segment it, break it into categories, and dimensionality reduction, where you want to find a condensed representation of your data. So we're going to be focusing on clustering in this talk because we don't have that much time. So when you want to cluster huge data sets or run any sort of machine learning algorithm over large amounts of data, you have two main problems. The first problem is designing a system that can process huge data sets in parallel. This is both a systems problem. You want to be able to abstract out all the low-level details of serialization, networking, fault tolerance from the user who's hopefully a data scientist and not some expert kernel hacker. It's also an API problem. How do you work at the right level of abstraction? And then second of all, given a framework that allows you to process huge data sets, how do you take advantage of it that works with algorithms that work well in parallel? So here we're going to sort of describe both of these processes a little bit, both like the framework API side and then how to adapt algorithms to a distributed framework to get a feel for what it looks like to write algorithms to process huge data sets. So the sort of canonical big data processing framework of our age is MapReduce. MapReduce has a bunch of advantages. It allows you to run your algorithms on local data. It pushes the code down to the data so you don't have to transfer it over the network. It handles all sorts of nitty-gritty distributed system stuff for you, like fault tolerance. And most importantly, it provides linear scalability. It forces you to write programs in a way that they can execute over huge data sets. MapReduce also has a few problems. Each job requires pulling the entire data set from persistent storage. There's no concept of a session or storing intermediate data in memory. And jobs follow this rigid map then reduce structure. So this makes MapReduce very terrible for a lot of the classic iterative algorithms that you see in machine learning. So enter Spark. Spark, which I think all of you are familiar with, is a general purpose computation framework geared towards MapReduce, like MapReduce, but it's more flexible than MapReduce in a few specific ways. The extra properties are, first of all, it's able to leverage distributed memory. So it has this concept of a session, this concept of like an application that lives over time, and within the resources of a Spark application, you can load data into memory and do multiple passes over it, which is important for iterative algorithms. Second of all, it allows you to write full directed graphs. So while MapReduce has this rigid map then reduce structure, with Spark you can have much more general flows of processing. And then perhaps most important, there's much improved developer experience. There's a REPL which allows data scientists to type stuff in and have stuff come out immediately. And it has language support in Python, Scala, Java that makes it a lot more attractive than just writing code in Java. So these are the sort of basic Spark concepts. I'm sort of going to gloss over them a little bit so we have time to get to the more fun machine learning stuff. But basically with Spark, the way it works is you define a Spark application, or you write a Spark application by defining a sequence or a graph of RDDs, resilient distributed data sets. An RDD either references some data in persistent storage or applies some sort of transformation to a previous RDD. So here what we're doing is we're saying let's create this RDD out of a text file and persistent storage. Then let's take that RDD, transform it into a new RDD in which we have interpreted each line of text as a number. And then last of all, we have this action we call numbers.sum, which is going to compute local sums for each of the partitions over our data set and then pull them into our driver and finally sum them together to compute a full sum over the entire data set. Spark basically has this idea of caching, which at any point along this pipeline, you can say, take this piece of intermediate data, and instead of just discarding it element by element as it is computed, take that whole stage in the pipeline and cache it in memory. So that after computing it the first time, the next time that you come back to it, the data will be there, and you don't have to go through the initial reconstructing steps to get to it. So here, the first time we save a bunch of data in all these partitions, and the second time we only have to go back to these partitions to compute our sum. So back to machine learning. Spark has this machine learning library built on top of it, which includes a bunch of implementations of algorithms that can scale to large data and use the Spark runtime underneath. And this library is called MLlib. This is sort of the current state of MLlib. I think it's actually a little bit out of date right now. For example, the random decision forest, which is listed as soon, is no longer soon but exists. Inside MLlib, we're going to focus, as we talked about, on Kmeans clustering. So with clustering, the basic thing that we want to do is we have some data set, and we represent our data set as a bunch of vectors, as a bunch of points in some sort of high-dimensional space. In this case, our high-dimensional space is a two-dimensional space. But that just makes it easy to look at. We could use many more dimensions. And so given this cloud of points, some close to each other, some far from each other, we want to come up with a clustering. We want to group points together so that segments that are near each other are in the same clusters, and segments that are far away from each other are in different clusters. So this would be a sort of a nice clustering of this data. We have these three sort of clouds, and each of those clouds belongs to a different cluster. You'll notice on this picture we have these black dots in the center of each of the clusters. And this is something that's specific to Kmeans clustering, which is sort of the most common method of doing clustering. Each of these black dots is a cluster center, and the centers define the set of points which comprise a cluster. For any point, you figure out what its cluster is by saying compute the distance to all the centers that are in our clustering model, and the one that is closest is the cluster that point belongs to. What would we want to use K-means clustering? It's great for things like anomaly detection. You can consider anomalies as data points that are far away from any cluster, or possibly have clusters that sort of characterize bad behavior. It's useful for feature learning. Instead of using, so like for example, data that looks like this might be hard to separate. Linearly, you can't draw a line that cuts away the blue points from the red points. But if instead of using that space and you transform it into a space in which you remap every point to the closest cluster that it's in, then it's much easier to separate. And it's useful for a few other things as well. This is what it looks like to use K-means clustering in Spark. This is a simple Spark application that will read a data set from a text file. The second line up there, you can see we have parsed data, is formatting the data, interpreting it as numbers instead of as strings, and then we simply define a number of iterations that we want to run our algorithm for, define a number of clusters that we want to find, and then have Spark go to town on it. So how does this work under the covers? The K-means algorithm relies on this concept called a Lloyds iteration. And within each Lloyds iteration, there are two steps. At the beginning of an iteration, we assume that we have some sort of initial clustering. So a clustering in K-means revolves around a set of cluster centers. So we have an initial set of points which constitute our initial cluster centers. And we'll talk a little bit later about how we actually come up with the seed set of points, how we bootstrap, how we come up with the initial set of points to start our algorithm. But we'll just assume that we have a set of points so far. So within a Lloyds iteration, we look at all the data points in our entire data set. And for each data point, we say which of the cluster centers in our current set is this data point closest to. Doing that over the entire set of data points will give us essentially a clustering of our data set. By clustering, we mean that we'll have assigned each data point in our data set to a cluster. Given this clustering, now we can say, okay, let's look at each cluster. And is it the case that the previous cluster center that sort of defined which points ended up in this cluster, is it the case that that's actually the optimal cluster center for this cluster? Is it the average of all the data points in this multiple dimensional space? So what we do is then instead of holding the cluster centers constant and the assignments variable, now we hold the assignments constant, and we refigure out the cluster centers based on that assignment. So we recompute the cluster centers, basically doing an average of all of the points that have ended up together in the same cluster. What does this actually look like on the data? So here's our data set that we're messing around with. Here is an initial clustering. We have these 3 random black dots which represent the cluster centers. we can see it's not that good, right? That little chunk over there, which we think should be a single cluster, sort of split between these green and blue categories. So we reassign everything based on our cluster centers, and then we recompute our cluster centers based on the assignment, and that gives us something like this. So that's our first iteration, gets us most of the way. The second iteration is doing the same thing, but it has a much more subtle effect. The only material change is to change the assignment of that little point that are pointed to by that nice little pink line. And so there's our final clustering. How does Kmeans work on huge data sets? So Kmeans is actually super parallelizable if you just think about the basic algorithm. We talked about we alternate between these two steps. For the first step, we assign each point to a cluster center based on the existing centers. So that's basically fully parallelizable operation. We can consider each point in our data set independent of the other points that are out there, and process each data point independently. Then we want to recompute the cluster centers from the points in each cluster. This doesn't have this nice independence property, but it does have a property that allows common frameworks like MapReduce and Spark to tackle it really well. Basically, you perform an aggregation where you compute for each of the partitions of your data distributed over your cluster. You compute an average or a new center based on the points in those clusters within that partition. And then you have a fairly small amount of data that you can send to some central node or repartition, and through that complete the average on the full data. Take an average of averages weighted by the number of points within each average. So this is what the code actually looks like in Spark. For the first step, what we're doing is we're defining this map partitions function, which will take a bunch of take all of the data points within partitions, assign each of them to a cluster. Then we have this reduce by key, this aggregation operation, which allows us to perform the averaging. So this is all super fine and dandy, but there's one problem. How are we doing on time, by the way? 2:23. Okay, we'll be okay. Kmeans is very sensitive to the initial set of center points that are chosen. This is sort of a bad final clustering that results from choosing center points, choosing initial cluster centers that are no good. This is the final state. Kmeans isn't going to give us anything more optimal than this unless we restart and choose some new points. And further, there are nice algorithms for choosing centers, for choosing the initial set of centers that make you likely to get a good clustering. But the existing algorithms have been highly sequential. So the sort of state-of-the-art sequential algorithm is known as Kmeans++. The idea with Kmeans++ is you start with some random point in the data set. One of the random points is, so you choose as a cluster center one of the points that already exists. Then you pick another one randomly, but it's not fully random. Instead, you weight the probabilities for each of the points based on the distance from the point that's already chosen. So basically, you prefer points that are farther away from the point you've already chosen, in order to weight yourself towards getting a more even distribution over the full set of points that you have. You want to sort of have a sketch or a representative set of all the points, so you're not leaving out any regions unattended. So having chosen that second one, you basically repeat. You choose a third one, weighting by its distance from both of the two existing points. And you repeat until your k initial centers are chosen. So while this sounds like some crazy heuristic that someone would just think up because it sounds cool, it's actually proven to have some nice mathematical properties. The initial clustering has an expected bound of O log k of the optimum cost. And then you can improve that further by actually running the set of Lloyds iterations. What sucks about this is it requires k passes over the data. To randomly sample that next point, you have to consider every point in the data set, which if your k is high, which often with big data it is, it'll be like 4,000, that can be a lot of passes over the data set. So how do we solve this problem? This guy at Stanford came up with this idea, this basic extension of the Kmeans ++ idea, and he called it Kmeans parallel. The basic idea of Kmeans parallel is to instead of do a pass for every initial center that you want to sample, do only a few passes. I think 5 is the amount that's often used. With each pass, instead of just picking a single point, pick a bunch of points. So on each pass, you have some set of already chosen initial clusters, and then you're going to pick a new set of points to add to your set of initial clusters, and you're going to pick that new set of points based on distances from the old set, the old full set of initial clusters. So you're not going to be using the most up-to-date data. Like for example, if in a pass you choose 5 new points to add to your initial centers, you're not going to be using the locations of those points and trying to choose those 5 new points to be far away from each other, but you will be far away from the existing set of cluster points. Second of all, oversample. So choose, when you're done with all these 5 passes, you won't have k points, you'll have like k times 5 points. Then finally, run Kmeans ++ locally on the sampled points on this sort of oversampled set of points to find the k initial centers. So what does this actually look like visually? Again, we have our data set here. We pick one random point to start out with for our first pass. Our second pass is going to sample, in this case, 5 points based on distance from that single point. So over here, we can see that all the points that we sampled are kind of far away from the initial green point. Kind of hard to see that we chose. Our third pass is going to consider both the green and all the red points and sample based on distance from those. And so we finally have this set of green, red, and yellow points. I think maybe 15 in total. Now we want to bring those down to 3, to our preferred k. So we get rid of all the other points. We pull those down locally. We run a local Kmeans algorithm using Kmeans ++ on these points. Do some stuff, move them around. Then finally, with these 3 centers that we've chosen from that, we recluster on the full data and get a beautiful initial clustering. Cool. Thank you.
We may have time for 1 or 2 quick questions.
So in one of the very first slides that you showed was actually how to call the Kmeans function, and you had to pass in the number of iterations and the number of clusters that you wanted to find. Is there any smart way of doing like some kind of convergence test so that you know how many iterations you should be running?
Should I repeat the question? So the question was, yeah, at the beginning we need to pass in the number of iterations and number of clusters. Yeah, I mean, so basically you can see at each point you can compute a cost, and that'll be like the full like cost function of how good your clustering is. Once the cost isn't really changing that much between iterations, then you stop. So the number of iterations there is actually a max iterations. Spark's implementation will try to terminate before that if it can. Yeah, exactly. So that actually is happening. It will try to converge. Just like if it has trouble converging, that's the maximum amount of time it'll spend. Any more?
All right, thanks a lot.
Cool. Thanks a lot.